In the last video, we finished up this question here, and what this question was asking, what it was asking us to determine the relative boiling points of these four molecules. And what we figured out was that the larger molecules, like the tin hydride, would have higher boiling points than the smaller molecules, like methane. The main reason being that the dispersion forces are a lot stronger with the tin than they are with the carbon-based molecule because it's so much bigger. There are more electrons to push around. It's easier to polarize the molecule, and so therefore the dispersion forces are larger. And so because of that, the attraction between the individual molecules is larger, and so therefore it is more difficult to boil it. Again, this is our logic connections here. The higher the boiling point, the stronger the forces between the individual molecules. And that's the case because if there are strong interactions between the molecules, then you have to put in more energy to break the molecules away from each other, which means that it has to be at a higher temperature. The boiling point is going to be higher. So if we look at this table of the hydride, if you want to call it that, form of all the different elements here. So this is just the elements from the periodic table, at least in one section of the periodic table, bonded to hydrogen. And we can see the four that we just looked at here, CH4, SiH4, GeH4, and tin H4, and it's doing exactly what we thought it was going to do. The lowest boiling point is methane, and as you go to the next largest molecule, to the next one, to the next one, the boiling point just gradually increases. And so that makes sense based on our knowledge of dispersion forces. And if we look at these other data points here, for the most part, they also follow that same trend. And so this is split up into the groups from the periodic table. So, if we have our periodic table here, here. So this is our periodic table. So we have group 7A, 6A, 5A, 4A. It's just the atoms up here in this corner of the table. And so group 7A for these three molecules here, very, very similar. Same thing with 5A and 6A for these three molecules. As the molecules get larger, the boiling point gradually increases. So, what the heck is going on with these guys? If all the other molecules are following the trends that we've seen so far, what would make these three have such drastically higher boiling points? Much higher. Like water here, for example. Water is tiny compared to tin H4. This molecule, in terms of the number of electrons, in terms of the mass, just the tin by itself is several times larger than the water. So how is the boiling point of water so much greater than any of the rest of these? The answer is that those three molecules participate in a special kind of intermolecular bonding. They have a special kind of intermolecular force that they participate in called hydrogen bonding. Now, in reality, this is just a dipole-dipole interaction. But it's just a dipole-dipole interaction. That's like saying that, the ocean is just a big pool. It's maybe a bit of an exaggeration, but it's, hopefully gets the point across. Hydrogen bonding technically is just a dipole-dipole interaction, but this type of dipole-dipole interaction is significantly stronger than the other ones that we saw in the previous video. So this type of interaction only takes place when you have a hydrogen bonded directly to an oxygen, a fluorine, or a nitrogen. So not that you have hydrogen and one of those three in the same molecule. The hydrogen must be directly bonded to one of those three things. Now the fluorine isn't really going to come up very often after this because, truth be told, this is the only molecule where this is possible. Because fluorine only can form one bond. Well, technically it can do more than one, but it is extraordinarily difficult to get it to form more than one bond, and we're never going to see it happen. So this is the only molecule we will ever see where fluorine has a hydrogen bonded to it that is participating in hydrogen bonding, just because once you have the one bond to fluorine, the molecule is done. There's no more molecule from that point. But the oxygen and the nitrogen we will see fairly often. So if you have a hydrogen bonded directly to the oxygen or directly to a nitrogen, you can have hydrogen bonding occurring. And so where this occurs is between the hydrogen that is attached to, in this case, the oxygen, and because the dipole here between the hydrogen and the oxygen is particularly strong, because the oxygen has a particularly high electronegativity, this has a particularly large positive partial charge. Again, it is just a partial charge. It is not a whole charge, but it is a particularly strong partial charge. And so the hydrogen here will then be attracted to the oxygen on a different molecule that again has its own partial negative charge. And so this positive to negative interaction, these opposites attracting, is actually decently strong. Not as strong as an actual chemical bond, but in terms of intermolecular forces, it is quite strong. And so, like I said, the only molecules where this will happen with fluorine is in HF, but in oxygen and nitrogen, you'll see it in lots of different places. This also can, as you can see here, we can get lots of these molecules kind of lined up, so to speak, and we'll see that again in just a second with water as well, where these hydrogen bonds can actually affect the orientation of the molecules. Actually, we're going to see that right here. So I have a nice little Calvin and Hobbes cartoon for you here. Why does ice float? Because it gets cold. Ice wants to get warm, so it goes to the top of liquids in order to be nearer to the sun. Is that true? Look it up and find out. I should just look stuff up in the first place. You can learn a lot talking to me. It is not true. I forget what the dad's name is, but he's just making stuff up there. The real reason that ice floats is that when you're freezing water, the water in the liquid phase, the molecules are all jumbled up next to each other. They're bumping into each other and moving fairly rapidly, and they're constantly making and breaking hydrogen bonds. But then when you start to freeze it, when you start sucking the energy out of it to where it doesn't have the energy to be bouncing around and making and breaking these bonds, it's going to orient itself to maximize those hydrogen bonds. So the water molecules, as they lose their thermal energy and they get stuck into place, they're going to orient themselves so that they have their hydrogens pointed at oxygens and their oxygen pointed towards hydrogens. They're going to orient themselves to maximize those intermolecular forces. In this structure, where all the hydrogens are pointed at oxygens and the oxygens are pointed towards hydrogens, that structure actually causes the water to be a little bit more spread out than it was in the liquid phase. Because again, in the liquid phase, they're bumping into each other and constantly making and breaking bonds. So they're actually closer together in the liquid phase than they are in the solid phase. And so when it freezes, because the actual molecules themselves spread out just a little bit to increase those intermolecular forces, the ice is less dense than the liquid water. And if you remember your Chem 1, things that are less dense float, and things that are more dense. This is why, if you have kids and they have those little numbers and letter foam things that they play with in the bathtub, the reason that those things float is not because they're made of foam. It's not some thing that is just intrinsic, like all foams float. It's nothing like that. It's just that it's less dense than water. That's the reason why it floats. Anything that is less dense than water will float in water, assuming it doesn't mix in. Like there are some liquids that would be less dense than water, but they don't float because as soon as you put it into the water, it just mixes with the water. So if it's something that won't mix with the water and it's less dense, it will float. If it's something that won't mix with the water and it's more dense, then it will sink. That is just the way that density interacts with gravity. So that is why ice floats. And this is actually incredibly important. It's not just some interesting side note to life here on Earth that ice floats. Life on Earth would probably not exist at all, actually, if ice did not float. If ice was more dense than liquid water, every winter, for all of the planet that has winter that can freeze ice, and if you go back far enough, that was the whole planet. During the Ice Age, the whole planet got cold enough to freeze water. If it was cold enough to freeze the water, then fresh water sources like lakes, as soon as it got cold enough to freeze the ice at the top of the lake, that frozen water would then sink to the bottom, which would then expose more water to freeze and sink, and more water would be exposed, and it would freeze and sink, and you would completely freeze this fresh water that animals and people used for drinking water. But as it is, if the top of the lake freezes, well, you still have plenty of liquid water down below that you can get access to, that things can live in. This is how you can have lakes up in Canada that the tops of it freeze solid every year, but things are still alive in the lake because there's still liquid water down below. But if the entire lake froze, well, you're going to have a bit of a harder time staying alive in solid ice, for sure. This is also really important for things dissolving in water. The reason why water dissolves things so well is because it's so polar. If a molecule is even slightly polar, it will at least partially dissolve in water, and very often it will completely dissolve in water. It will be what we call totally miscible, which we'll talk about in the next chapter. This is also really important for biological systems like DNA. Hydrogen bonding is actually what holds your DNA together. It is literally the interaction that keeps you zipped up at the genetic level. The interactions between the base pairs in your gene code are actually hydrogen bonds. There are hydrogen bonds between, or for the most part anyway. Some of them aren't 100% hydrogen bonds on both sides, but it is, for the most part, hydrogen bonding here that holds those base pairs together, and that interaction is just strong enough to hold the DNA together, keep it from unwinding, but is just weak enough that when I think it's called helicase, I think is the name of the enzyme. I think it's an enzyme. I'm really not a biologist or a biochemist. But I believe it is helicase that comes along and breaks the DNA apart and copies it. So the DNA needs to be held together to keep it from unwinding and just being unusable, but it can't be held together so strongly that it can't be unwound and copied. And so hydrogen bonding is right there in the sweet spot, where it can hold your DNA together, but not so strongly that it can't be separated again. So hydrogen bonding is actually incredibly important. In multiple ways, you would not be alive without hydrogen bonding. All right, so let's look at a question here. Consider the compounds dimethyl ether, ethanol, and propane. Their boiling points, not necessarily in order, are -42, -24, and 78. Match each compound with its boiling point and explain your reasoning. So we have CH3OCH3. Booze. Oh, wait. I was writing that out incorrectly. Sorry about that. That's ethanol. And then propane. So go ahead and take a second here, pause the video, think about these three molecules, think about the types of intermolecular forces that might exist in each of these, and try to match up these three boiling points with those molecules. So go ahead and pause the video now and give that a shot. Alright. Hopefully you paused the video and tried to work that out on your own. And hopefully when you did that, you realized that the key here is that the molecules with the strongest intermolecular forces are going to have the highest boiling points. So again, the stronger the interactions between the molecules, the more energy you have to put in to break them away from each other, which means the higher the boiling point will be. The higher the temperature has to be before it boils. So if we look at the different molecules, this molecule only has dispersion forces, because the only bonds that exist here are between carbon and hydrogen, and between carbons, which are all nonpolar. So this would have the smallest amount of intermolecular forces, and so this would be the negative 42.1. When we compare these two, both of these have polar bonds. So just to, well, let me draw it a different way. Let me draw a Lewis structure here. So this is what the, sorry for my sloppy Lewis structure. So that is a dimethyl ether, and the ethanol would be something similar, only it would have the oxygen at the end attached to a hydrogen here. So both of these have polar bonds, and this is a polar molecule, even though if you just look at the Lewis structure, it looks like it might be symmetric, and so you might be tempted to say, oh, it's not going to be polar, but it is actually polar. We can't really use our rules from the previous video on this because it's not a very small, simple molecule, but you can just take my word for it that this is a polar molecule. This is especially, you can see it if you look at the 3D model, because it's not nice and 90 degrees like we have it here. All the bonds aren't 90 degrees away from each other. But anyway, this molecule has hydrogen bonding, and the other one doesn't. This only has dipole-dipole. And so because this molecule has stronger intermolecular forces, this will take a lot more energy to break apart than this one. And if you heard me say that this molecule was booze, this is alcohol here, what we commonly refer to as alcohol is chemically referred to as ethanol, then you probably could have figured out pretty easily that that was the one that was 78.4 degrees C, because if you've ever seen or had something that was completely or mostly ethanol, which I would not suggest, by the way, pure ethanol is a terrible, terrible thing to drink. I don't say that from experience. I just say that from chemical knowledge. Do not drink pure ethanol. It's a very bad idea. But if you've ever seen drinks that are almost completely ethanol, which those are actually not all that uncommon, you can get things that are really, really high percentage ethanol. They're not frozen. Or sorry, they're not in the gas phase. They're in the liquid phase, because these are all the boiling points here. So if we had picked negative 24.8 as the boiling point, that would mean that if we're higher than that temperature, the molecule is in the gas phase. And ethanol is obviously not in the gas phase at negative 20 degrees C. So you probably could have figured it out just by logic as well, at least for which one the ethanol belongs to. But the other two, we did have to think about the intermolecular forces. All right. We'll leave it there for this video. In the next one, we'll look at our last type of intermolecular force, which is ion dipole, and move on from there.